off into chapter 13. So it starts with some statics. So I guess you'll just have to be honest with me. It's not a lot of statics, but they do start with types of supports and reactions, that kind of stuff. So, you know, roller gets one reaction type of thing. So when we did supports and statics, we went through these quite a bit, and then we used them quite a bit. So this should be, although it's a ways back, it should be fairly current, because what we're going to do is shear and bending moments in beams, and that's so we then can do stress in beams. So just a little bit of statics. The statics does go internal to the beam, where in statics class we didn't go there, right? We just stayed external to the beam. So you kind of got to do a little beam analysis in statics before you go off and determine bending moment. Once you get bending moment, that's the internal force inside the material, then we can get bending stress. And that's our goal, okay? So rollers, anything with, you know, wheels, that kind of thing is going to get one reaction. Pin or knife edge, pin, it's going to get 2, X and Y, and then fixed is going to get 3. So this is the easy one to forget. Gets a X, Y, and a moment. So like a flagpole or a telephone pole, we embed them in concrete, and that's so they can take this rotational thing, right? We don't do that with bridges. I mean, we have a bunch of concrete, but then we pin the bridge to the concrete, right? So really the only time that we have something super solid and fixed, it's like some kind of welded thing, you know, stick something on the wall, weld it, bury something in the wall. Sometimes you'll see cantilever beams coming out of walls, you know, that have been built into the wall or the structure. Any of those kind of things will carry a moment. So they give you kind of the overall basics of what we work with over here. Types of beams. So simple beams just have the supports at the ends, right? And some kind of load. Remember, we can have a concentrated load or a distributed load, either one. Anyone remember how we deal with a distributed load? What do we do with that? Yep. We concentrate it, right? Essentially, we take a distributed load and we concentrate it. So the way we do that is what you described, is it's the area of the load curve. You've got to calculate the area of the load curve, and then you got to find the geometric center of that area. If it's complicated, if it's, you know, if it's got a bunch of geometry to it, then just break the geometry down and do those independently. So if you have a, John, using my pins. You have a beam and maybe it's got, you know, something like this, kind of a load thing to it. And the loads can come in all different shapes. I mean, they can be parabolic curves, a bunch of stuff, right? Break it into simple shapes. So this, I might break into like a triangle, a rectangle, right? 3 shapes. And then concentrate each one of those. This one for this shape, this one for this shape, this one for this shape. Keep it simple. Don't try to deal with the entire load as one geometric shape. That's a bit complicated. But we do concentrate them, and then we can do our some forces in the X, and some forces on the Y, and some moments. All right, let's keep going. Cantilever beams look like this, right? So that's a cantilever beam. It should get an X, a Y, and a moment. But since there is no X force out here, they just eliminate it in this cantilever beam, which is fine. There's no X forces. There won't be any X reactions, right? Same with that propped cantilever beam. A cantilever with a prop on the end gets a Y force for the roller, should get an X, a Y, and a moment for the fixed, but there is no X forces, so they just eliminate it. And then those P's are the external forces, right? The forces that are given on the problem. So Read through this if you don't like, if statics has been a while or you just don't recall it, refresh yourself on it, because we kind of need the concept of summing forces in the X and summing forces in the Y to do this internal force analysis of a beam. Yeah, then it goes into beam reactions. That whole chapter is like statics review, or the whole first section is statics review. Then it goes into shear force and bending moment, and that's where I want to start. So shear force, bending moment. So the reason we want them both is because we're heading towards bending stress and shear stress. Okay. When we do beam analysis, the two things we focus on is bending and shear of the beam. So just a simple one, making this totally up, so don't try and look it up anywhere. And I'll give us a little bit of, we'll say it had a roller there, and we'll say it had a pin here. And I'll put in the X just because that's kind of good symbology. And then I'm just going to put a single load on it. We'll put 500, and we'll put 5,000 pounds. So I'm going to locate it 6 feet here, 2 feet, and 3 feet. All right, and we'll call this a Y, B, Y, B, X. So had a roller here, but I removed it. Had a pin here, but I removed it. Made the free body diagram. That's what we called them, free body diagrams. So what we're heading towards is like, is this beam safe, right? How much bending stress does it have? How much shear stress does it have? And how much does it deflect? Those are the three things that we're going to try to determine before we say, yeah, it's good or not good, right? So deflection, that'll be down the road. Bending stress will be actually, I think, is the next chapter. But I'm going to start to blend it because we might as well. As we learn bending moment, we can then just think about bending stress also, okay? So the first thing is, on these kind of problems, is we have to determine these reactions, and that's the statics part. So there was 3 equations, right, to equilibrium. What were they? Yep. If all 3 of these are true, if they all equal 0, then we are in equilibrium. So essentially, we are putting this thing in equilibrium by saying, hey, this is true. This has to be true, okay? And then we just look for the opportunities that are easy first and then work towards the unknowns, right? So we always try to look for some direction where there's only one force, because that force has to be equal to 0, which we have. Which one? X. So Bx is equal to 0 because there is no other force in the X direction, right? A lot of times this is true if we're not thinking about wind or we're not thinking about seismic, okay? And we're not thinking about seismic yet, so. All right, so then what do? We can think about forces in the Y, but how many unknown do we have? 2. So no need to go there. You'll just end up with an equation with 2 unknowns. That means we got to do a moment somewhere to try and get BY and AY. And we recall that moment equals force times distance, and that needs to be a perpendicular distance. So if we just choose a spot, either A or B, we will drop that reaction out because it goes straight through the point. So if I choose to do a moment here, this would have no lever arm, no distance. So the moment for that is 0. The moment for that is 0. Obviously, it's 0. So those 2 are going to drop out of the equation. Recall that? Yep. All right, good. So let's do that. Moment at B. What are all the moments at B? Yeah, times its distance, 6 feet. So force times distance, and rotation is clockwise, which is negative. So the sign of a moment is which way it rotates. If it rotates that way, clockwise, it's negative. If it rotates around the other way, then it's positive. And it's always about the point that you choose. We're choosing point B. So 5,000 rotating about B, that's clockwise, it's negative. AY is going to rotate counterclockwise about B. So it's going to be positive AY times 8 feet, the perpendicular distance to the point that I choose. Right? And you definitely want to put AY in. That's your unknown, so you have something to solve. We set the equation equal to 0, which means equilibrium, and solve for AY. What'd you get? $3,750. Very good. And now we can get BY, right? Because we just know that all the forces in the Y have to balance out. So we got 5,000 coming down. We've got AY going up 3,750. We need another amount to equalize everything out. 1,250. Yeah. All right, there you go. Statics crash course. For some reason it took us 12 weeks to learn that, but it did. Thing is, I think we learned it. That's good. All right, so now beyond statics is bending moment. Like this thing's gonna deflect. It has 5,000 pounds on it. I don't know what it is, right? I would need to know what it is to calculate a bending stress, but I don't need to know what it is to calculate a moment, an internal moment. So inside this beam, so I always draw the deflection curve. A lot of times I do it in my head, but in this case, I'm gonna draw it and I'm gonna exaggerate it. Probably gonna do something like that is what the beam's gonna do, right? It's gonna deflect down where that load is. So in here somewhere, actually all along the beam, there is an internal bending moment. It's being bent. And all of the fibers inside the beam are resisting that, hopefully. And they're resisting it easily, hopefully, or else you have the wrong size beam or the wrong material, right? But that's where we're headed, is like, hey, is it resisting it? Can it resist it? What's going on inside there? So that's what we want to try to figure out is, hey, what is going on inside there? So we need to know what that internal moment is. And it is a moment. These things are trying all to rotate. If you went anywhere along here, you could calculate the internal moment. We could do it, okay? So if I go at 2 feet, I can calculate what's going on inside the beam just by cutting it, drawing a new free body diagram, and putting it in equilibrium, because it is in equilibrium. It's deflecting, but it's not going anywhere, hopefully, right? That's what we're hoping. So the way you get internal moment and internal shear force is you section it at the spot that you're interested in. Like what's going on here at 2 feet. So to do that, I section it and I draw, and I typically work with, and I'll actually show that as a cut. I work with the left side. I'm not sure the book says, hey, you have to work with the left, because you'll get the same answer if you work with the right. But I just always work with the left, and it keeps things kind of straight for me. So I draw my 2 feet of beam, and I include all of the external forces on it, which is BY, 1,250. Once you get that piece of beam drawn, like I'm not including the 5,000. That's not on my piece. I'm not including the 3,750. That's not on my piece. If there was a distributed load over this area, I would include 2 feet of that distributed load, right? But I don't have that either. This is all I have, is my little 2 feet and 1,250, okay? And what I wanna know is at 2 feet, what's my internal, and I always write a little 2 feet next to it. What's my moment at 2 feet? And literally all you do is find the moment. If there's a bunch of forces, you got to find all the moments and add them up. But I only have one force, right? 1,250 times 2 feet. 2,500. And that is foot-pounds. Make sense? At any point you can do this. You can do it at 2 feet, at 4 feet, at 6 feet, at 8 feet from the left, at 10 feet from the left. At any point you can do it. But that's how we know. So this moment, the 1,250 times 2, that's this moment out here, 1,250 times 2, correct? That's what it's trying to do about this point. So the internal resistance is always equal and opposite to that. Right? Does that make sense? It's got to resist it. They can't be both going the same way. It would spin off into oblivion, right? And also it's doing this to the little beam piece. It's deflecting it concave up, right? And that's what we think was happening up here by our deflection curve. We can see, oh yeah, it's definitely concave up. And this thing would also be concave up. So that's good. That's confirming what we're thinking is going on. The moment at 2 feet is 2,500. What would the moment be at 4 feet? Yeah, 4 times 1,250, right? Yep. All right, what would it be at 6 feet? Yeah, just keep, 6 feet's only 2, so we're right in here somewhere. Well, originally from the left to that load was 6 feet. Oh yeah, so right at, this would be at 6 feet, correct? Yeah, so let's do it at 6 feet, because that is an interesting thing to look at. 6 feet. Still have our BY force of 1,250. Now the 5,000 shows up. So I'm putting it on, right? That's at 6 feet. Anything else on that piece? It's this piece right here, yeah? And again, you're right, that 2 feet is just where I sectioned it. So we have 6 feet of total. Right, everyone agree with this? It's good? And this is a cut. Usually try to put like a cut thing in there. So check it out. I want to know the moment here, right? I want to know the moment at 6 feet. So what are the moments about this point right here? 1,250 times 6 and 5,000 times 0. So really the 5,000 doesn't show up yet in the moment. Okay, so I'm just going to crunch that. 1,250, enter. 6 times 7,500. And remember, it's going to resist, so it goes that way. And that's foot-pounds. All right, good. Let's do it at 8 feet. So just before 8, this is just showing up, AY. So you do it at 8 feet and I'll confirm it. So now we are 6 feet to the 5,000. And then we are at 8 feet here. So that's another 2 feet. And AY does show up. tricky. I didn't plan that one. I had to run that one twice. I'm like, what? Really? Oh, that's cool. What do we get? 0. It does. Look at the deflection curve. Yeah. And this actually, I'm going to say it's probably straight because there's no load out there. So the deflection all happens between here and here. This is what we call a transition point. Oh, this is what we call a transition point. And then this little piece of the beam, it's rotated, but it's straight. It's not going to do any kind of curve out there. So that means if we just kept going, we would continue to get 0. That's trippy. At least it's kind of trippy for me. So let's do it at, what did they used to say, 3 feet? So we can do it at 10 feet, right? 6 and 4. Yeah, let's do it at 10 feet. I think it used to say 3. But it doesn't matter. We're going to do it at 10 feet. Yeah. So really, we can just kind of use this thing, and extend it because there's no more forces that show up. So we can kind of just extend this out to 10 feet. Everything goes up by 2 more feet, right? 1250 times 10, 5,000 times 4. It's going to come out to 0 again. Still out there. Sure. Yeah. It's all 0. Absolutely. So if you just took this section and do a free body diagram of it, right? That's what you're saying? 3 feet? Looks like that. It's a lot of nothing. Yep. All right, very good. So the other thing, that's the moment. The other thing we want to think about is what's called the shear force. So the moment is the internal rotation of the beam. The shear force is literally a force vertical up and down that also occurs, that is trying to literally shear the beam off. So that happens in beams, and we need to think about that. It's not usually the control. It's usually a secondary thought, but this is how you get it, by sectioning the beam. Same thing. So when you section it for your moment, we can also think about the internal shear force at that location. The shear force is just a force. It's not a moment. It's a force, typically an up and down force, but it depends on what you have out here. So in this case, we have 1250 out here. Essentially what you do is you say, okay, I have to say some of the forces in the Y is equal to 0. That's got to be true. There are no X forces, so I'm not going to worry about that, but there is a Y force, right? That Y force is going up at 1250. The internal shear force, which we call V, has to balance that. So this is the force that's literally trying to shear off the beam. It's usually on a stress level, it's usually magnitudes lower than bending stress. So it's not typically a control, but we always check it. We always check this shear force and shear stress. Okay. So it's just the force that balances whatever is going on to the left. Now, there's a new sign convention for it. Yeah, I know. So we have forces going up, they're positive. Forces going down, they're negative. We learned that like in the beginning of statics. Forces to the right are positive. Forces to the left are, yep. Moments that rotate this way are negative. Moments that rotate the other way, that way, positive. So those are the sign conventions we've done so far. Now we have shear. So shear is two forces. An up down, an up force and a down force, right? And it can be either this way or it can be this way. Those are the only two combinations, right? If the left side is going up, this is how I remember it. If the left side is going up, it's positive. If the left side is going down, it's negative. So the beam force controls it for me. Like that's how I can remember this stuff. And it actually does become important when we think about that internal force. If it's going up, then we have concavity down, like it's humped over, right? If that internal force is going down, then we have a deflection down and concavity is up. And concavity is going to be kind of important when we do deflection. So in this case, we have left effect up, right effect down. So this is a positive. So it's like opposite of what you see here. But we don't get the shear force sign from a direction. We get it from a combination of two forces. So this is positive. And then you do the same thing at every location. Like here at 6 feet, I sum the forces in the Y. The 5,000 does show up. It's because when we're summing forces in the Y, we don't care what those forces are, right? So we have 1250 up, we have 5,000 down. What do we need to put inside? Should be 3,750, right? And it needs to be up to balance it. Correct? Yeah. So what's the effect of the beam? The beam effect is down, because this and this say, oh, there is a downward force out here. This is balancing that downward force. So this is beam effect. Yeah, so if the left side's down and the right side is up, we are negative. Shear. Yep, yep. And it is a force. And you'll see that this number is going to drive up the closer we get to supports, because that's where all the shear gets maximized, is right next to that support. So essentially it's saying, okay, shear stress and shear failure is saying, all right, we have a beam and it looks like this, right? But potentially it could do this and just fracture right here, like just shear off if that force was great enough. And if that force was close enough to that support.
So it's more likely to break in the support than it is.
Absolutely, than in the middle, correct. Due to shear, under shear, yes.
Okay.
It's more likely to fail in bending, break in bending, in the middle, in the span. Yeah, yep. And like I said, we never design in shear because shear is almost never a problem. Like it's just not a problem. Bending is our typical problem, but we always check it in shear. That's just what we do. We want to make sure both are fine. All right. Yep. The bending effect, some of the moments for bending.
Oh, beam effect, sorry.
Yeah. The beam effect is the sum of the four. Yep.
And then so that, whatever direction that beam effect is the left arrow.
That's correct. The green arrow is the balancing. Can you see green? Does it look green? Kind of looks green. Yeah, that's the balancing of these two forces, or whatever forces show up. The single balancing force is this internal shear.
Right.
Yep, correct. Yep. So then we could do one more. We could do it here at the next support, because this will be pretty big here, typically. So how would we get V? Well, we have to figure out all that's going on out here. So we have a plus 1250, we have a minus 5,000, and we have a plus 3750. That's what's going on the beam. This V force will have to balance that, whatever that summation is. So then the V force is 0 in this location. So internal shear at this location is 0. That just means there's nothing, it's going to continue to be 0 all the way out just because this part of the beam's not loaded once you get past that support. So if we did it just before the support, like infinitely close, and that's actually a term the book uses, infinitely close to the support, but not quite to it, right? Then we eliminate this, and the shear force goes right back to 3750. So infinitely close to the support, shear is 3750. At the support, shear is 0. That's the huge spike. Like it goes from this giant load to nothing. Absolutely. Yep. Once you get it to a stress. Right now, we're just doing forces. Yeah. But yes, exactly. Yeah. Yeah. So here's the deal. That's a lot of work. And really, we don't need all this information. We need maximums. I don't really care what it is at 2 feet. And I don't really care what it is at 3 feet. What I care is where is it maximized and what's that number? Does that make sense? Just know though that you can get the moment like this anytime you need it, because the next step is to draw these diagrams that tells us where the maximums are, right? But if you're ever unsure, you can always go back to, oh, I'm just going to make sure that I've drawn this graph right. I can take a moment anywhere and figure it out, right? So the book, does it head there? I don't know if it heads there right away. No, it does what we just did quite a bit. Oh no, then it gets into it. Yeah, we have enough time because the shear diagram is super fun. Sorry, geeking out, but it really is super fun. The moment diagram is a little more complicated. So we do diagrams so we don't have to do it at 2 feet and 3 feet and 4 feet, to figure this stuff out. I just want to know where max is. So same beam. I'm going to draw the same beam again. And that'll help us verify our numbers that we just came up with. Make it a little longer. I have a support here. I have 5,000 here. It does help to draw them kind of graphically accurate. So when you draw them, make your 2 feet and your 6 feet somewhat right. And then 3 feet. And I do know that 3750 is here and 1250 is here. Good? I think that's right. So I don't know if it's a shortcut, but the way that we will do it, because it's much more efficient, is we will draw what's called shear and moment diagrams. And that will locate maximum shear. That was the V force. And it'll locate maximum moment for us. So we don't have to do the whole figure it out every 2 feet thing, right? So the way you do it is you draw it directly below the beam. And it's going to be a graph. The first one is shear. And this line is the 0 shear line. So like where we found 0, didn't we find 0 at this support for shear? Yeah. So I'm expecting it to just nail right there, right on the line. That is 0 shear. Above the line is positive shear. Below the line is negative shear. And I think we had both of those, right? So we should see some of that happen. And we may not get to it, but then the moment diagram is directly below it. And the super cool part is, okay, again, geeking out. Sorry about that. Really sorry. If you've had any calculus though, you'll dig this. This is the load curve. These these forces create what's called the load curve or the load condition. The derivative of the load curve is the shear diagram. And the derivative of the shear diagram is the moment diagram. Super geeky, but super fun. Fortunately, we don't have to do any of that stuff. We just can just draw them once we learn the strategy here. All right, so shear is the easiest. You literally follow the forces in the shear diagram because this is a force, shear force, right? So when you start the left, start here. When you come to a force, you draw it onto your graph, give it some scale, and make that scale kind of consistent in your head. I just do it by like, oh, 5,000 is going to be like my biggest thing. So when I draw a 1250, I'm going to keep it pretty small. And I literally follow the force. If it points up, I go up. 1250 pounds. If nothing's happening on the beam, if there's no load change, no distributed load, nothing going on, then that stays consistent until there is a change. So here's the first change at the 5,000. So it comes over and it is 1250 right there. Again, I just follow the force. And I'm going to drop a total of 5,000, which should put me down here at 3750 negative, which is what I believe we found at the 5,000, right? We found a negative shear force, 3750. And at 2 feet, we found 1250. At 4 feet, we found 1250. At 6 feet, we found 3750 negative. And then what happens? Nothing. It just stays horizontal until it hits the what? 3750. And then it goes up to, yep, up 3750 to 0. And then what happens in the remaining of the beam? Nothing. So it just goes straight lines out. Kind of confirming that nothing's going on out here at the 3 feet. So if I was going to calculate shear stress, I want to use the maximum shear force. The maximum shear force is always the biggest number, absolute value. I don't care if it's positive or negative, it's the biggest number on the graph. So that would be 3750 for max shear. So and it happens between here and here. Like if I really, if I want to know the spot, often the shear it's over a range of the beam that it happens, but it happens between here and here. So if I'm worried about it just shearing off, that's going to happen in this region, in this 2 feet, right kind of next to this support. Out here, it's much less. So shear force is pretty easy to do. Follow the forces. If it's a distribution, then you have to think about how much it changes with the distribution. So that can be a little more challenging. I can show you that. The moment diagram we create from the shear diagram. So, I mean, we can kind of start on it, but I'll probably do a whole hour on it. But since one is a function of the other, we can use the shear diagram to create the moment diagram. The shear is positive here, and the shear is negative here. Right? Agree with that? Positive slope is This is horizontal. Positive slope is uphill. Negative slope is downhill. If I think about a line or a graph, okay? This is telling me the slope of the moment diagram. So where the shear is positive and negative gives you the slope. So that means, oh, that means I know that the moment diagram is positive in this region. Again, you create your own scale. I could put it really steep if I wanted to, but I'm going to run out of space if I do that. So I made it pretty flat, but that's positive slope. And then somewhere right here, it dramatically changes to negative slope. So that means this travels like this. And yep, they're going to intersect, unfortunately. And it's only in this region it's negative because it doesn't exist out here. There's no positive or negative out here. So the moment curve is created from the shear curve, and it gives you the slope of the curve. And then you have to know other things, like you have to know that a horizontal line, when you differentiate it, turns into a sloped line. And a sloped line would turn into a parabolic line, a second degree parabola. And then the derivative of this is a third degree parabola. In other words, if I'm given a sloped load curve, then my shear is going to be parabolic and my moment is going to be third degree parabola. Whoa, that's a trip. But that's kind of what we learn. We'll learn that sequence. Horizontal creates a inclined slope line. Inclined slope line creates second degree parabola, which is the first kind of parabola, is the second degree, and then third degree parabola. Often we don't go this deep. The load curves don't get that crazy, but often we will get to second degree parabola. Like if you're given a load curve, which this is reasonable that we get some kind of a load curve that looks like this, right? Then the shear diagram could end up to be some kind of parabola and parabola. And then the moment diagram would be, again, a parabola and parabola, but this would be third degree. This is second degree, right? So, and we have to be able to like calculate the area under these, which is typically a calculus process. But since it's so common, front cover of the book, area of second degree parabola is given. And then there's area of nth degree parabola. So if you had a third degree parabola, you could use the formula to calculate area of third degree. So it's so common that they, for us, just took the calculus out of it because this is not calculus based, and it doesn't need to be. Like they're pretty simple formulas to get to area of under the graph, which that's how we're going to determine, like, because in this case, I would want to know, hey, in the moment, what is that point? First of all, where is it? Okay, I know where it is. It's right there at that 5,000. I maybe could have guessed that. That's where the most bending is going to occur under that giant load, right? But that's where the maximum moment occurs. And then now I have to be able to calculate it. So I could come up, just section it, which we've already done, by the way, and know my maximum moment. When we did it, I didn't know where it was. I didn't know it was at this 5,000 location, but there it is, right? Now that I have that, I can go off to bending stress and calculate it, determine if my beam's good. All right, that was a lot. You're going to draw some shear diagrams, but honestly, I encourage you to, like, hey, if it looks simple, go for the moment diagram too, just trying to figure out these slope things. Like, oh, the sign of the shear gives me slope. It has to be here. Notice I didn't worry about, like, oh, is it steep? Is it not steep? I don't care. Just get it in the right way. And then look, it goes to 0. It goes negative, comes down to here, and then it's 0 out here. Like, there's no sign out here. So this is all no moment out there. So we just start to interpret these things and be able to draw these diagrams, right? That's kind of the beginning. Whew, that was good. That was a lot. So we'll practice it. Any specific question right now? You just absorb that and do a couple. So the book has you, maybe I'll give you one of them. It actually has you do internal moment and shear by our first method. Hey, what's the moment at 6 feet? What's the moment at 8 feet? So that's good practice. We'll do one of those. So we'll do number 7, which is one of those. And then we'll do $12. So notice on 12, I actually have little arrows for you. There's an A and a B. So we'll make, this will be worth 20 points because essentially it's 2 problems, right? But this one says, draw the shear diagram for number 12. So you can go for shear, you have to do your statics first, right? Then go for the shear diagram. This one, number 7, just says, calculate the shear and bending moment at 4 and 7 meters. Okay, 4 and 7 meters. Oh, and that's up here. It's easy to do the wrong problem in this book. Yeah, super easy to do the wrong problem. So, okay, 7 and 12 out of 13. And we are done. Yep. Yeah, yeah. The whole thing will probably be worth 40 because it's got 2 in the first one, 2 in the second one. So lots of points here. Yeah, on a metric. Yep. All right. Question is when you have a negative moment. Yeah. Yep. It just, I mean, it just goes negative in the graph and it means concavity changes. So see if I can figure one out. So we'll do the one I just did where we have a support, a load. You don't even need numbers like when you start to do this. I mean, you'll never get it right without numbers, obviously, but